Hello everyone, my name is Alessandra Costantini. I'm a postdoc at UC Riverside and I graduated from Purdue University where my advisor was Bernd Ulrich. I want to thank the organizers of CHOM for letting me speak here. This is a really nice seminar. So in this short video, I'm going to give you a quick overview about my research. My main goal is to study the structure and property of Riesz algebras and fiber cones. This has mostly geometric motivations, coming from the study of singularities and rational maps among algebraic varieties. But also there are some interesting algebraic reasons why one want to study Riesz algebras and fiber cones, mostly related with the theory of integral dependence and multiplicity, which were the original reasons why Riesz introduced these objects in the mid-50s. So my work is organized into three main themes. The first is to study the Cohen-Macaulay property of Riesz algebras and fiber cones of modules. The motivation here is mostly from singularity theories. One is interested in understanding whether a Cohen-Macaulay scheme stays Cohen-Macaulay after blowing up. In general, you could ask similar questions for different kind of singularities. And the second problem is to determine the defining ideal of Riesz algebras of ideals and modules, which geometrically corresponds to find the equations defining the scheme corresponding to the blowout. And the third problem is motivated by integral dependence. When you're interested in integral dependence of ideals or modules, the two objects you need to deal with are Riesz algebras and minimal reductions. The core is the intersection of minimal reductions. This may be a priori an infinite intersection, so it's difficult object to calculate. For ideals, there is a good amount of literature based mostly on the theory of residual intersections. For modules, the problem is not that well understood, and this is the topic of an ongoing project with Louisa Foley and Ju-Yun Hong. We just started working on that. So in the rest of this video, I'm going to give you more details about the first two problems. So the Cohen-Macaulay property of Riesz algebras and fiber cones and the defining ideal of Riesz algebras. So let me start with the Cohen-Macaulay property. There is, first of all, a great amount of literature about the Cohen-Macaulay property of Riesz algebra of ideals. However, the problem for modules is not as well understood. The main result here is by Simic, Ulrich, and Vasconcelos in 2003, and consists in reducing the problem to the case of ideals. Starting with a module, one constructs a generic Bourbaki ideal associated with it. The key part of the theory here is that ideals are identifiable with torsion-free modules of rank 1, so the theory of Riesz algebra of ideals becomes a particular case of the theory of Riesz algebra of modules. However, there is no general technique known to study the Cohen-Macaulay property of fiber cone of modules unless these are ideals. And even in the case for ideals, the techniques used to study the Cohen-Macaulay property of the fiber cone are usually different than those for the Riesz algebra. And in fact, the Cohen-Macaulay property of Riesz algebras and fiber cones are usually unrelated to each other. So my main contributions to this problem are the following. In the first project, I provided sufficient conditions for a module to have Cohen-Macaulay Riesz algebra. Here I'm using the technique of generic Bourbaki ideals, and I'm extending some results that were known for Riesz algebra of ideals based on the theory of residual intersections by Johnson and Ulrich. And I'm generalizing those results to modules. The second project is with Tan Dang, and it's about the Riesz algebra of the module of scalar differentials. Here, we combine the information from the generic Bourbaki ideals with the information we can extract from the presentation metrics of the module of differentials. And we are able to characterize the Cohen-Macaulay property in terms of the height of ideals of minors of the given matrix. And finally, in the third project, I proved that in certain circumstances, the Cohen-Macaulay property of fiber cones can be studied using generic Bourbaki ideals. And this is going to be the topic of my talk at CHAMP. So if you're curious about the details, please attend my talk. And in the last slide, I'm going to tell you a bit about defining ideal of Riesz algebras. So here, the most important part is that much of the information about the defining ideal of the Riesz algebra is actually encoded in a presentation matrix, or more generally in a free resolution of the ideal or module we're constructing the Riesz algebra of. And in some cases, especially when dealing with ideals, one could exploit methods from algebraic combinatorics and representation theory to study both the free resolution and, as a consequence, the defining ideal of the Riesz algebra. And sometimes a preliminary step in order to understand the defining ideal of Riesz algebra is to explore the Cohen-Macaulay property. So somehow this problem is more difficult, and actually it's not known in general. Like, very few classes of ideals or modules have known defining ideal of, for the Riesz algebra. So my contribution is, in the first project, I describe modules of projective dimension 1 who have the Riesz algebra of modules of projective dimension 1, which have an almost linear presentation. So all the columns are linear, but one of the columns is homogeneous of arbitrary degree. And this extends result of Boswell and Mukundan, known for ideals. And then finally, in the last project, which is an ongoing project with Ben Rapkin and Lorenzo Guerrieri, we studied the Riesz algebra of ideals of star configurations in two cases. First is the case of monomial star configurations. In this case, it's a square-free monomial ideals with a super rich structure in terms of free resolution. And the second case is the non-monomial star configurations, where calculations are a little bit more difficult. And I think that that's all I wanted to say. I'll see you all at my talk.